This is a video for AQA Mechanics, Centres of Mass and Moments, section 1.3. We're looking at the centre of mass of a uniform lamina. By a lamina then we mean an object which can be modelled as a plane which has got no thickness. So it's really a two-dimensional object, which of course is a mathematical modelling idea. However, we're considering that this has a constant mass per unit area when it is a uniform lamina. Therefore, by symmetry, we can calculate the positions of the centre of mass of each of these objects. The line of symmetries, for example for a rectangle, tell us that the centre of mass will be this position here. If we've got an equilateral triangle, then we can see that these altitudes here will form the position of the centre of mass, again just by symmetry. And then for a hexagon, again drawing in lines of symmetry, we can see that they all cross at a single point, which will be the position of the centre of mass. So for example, if we have a thin piece of card, well, by thin card we're implying a lamina, i.e. no thickness, and therefore we can say by symmetry that the centre of mass will be at the point where these lines of symmetry cross. Then if by convention we take the bottom left hand corner to be our origin, then we can see that this must be at 6 and this at 2, and therefore the centre of mass here must lie at the position 6, 2 relative to that bottom left hand corner. We've already seen that for lamina in general it's quite easy if they are consisting of symmetric shapes to find the positions of the centre of mass. The hexagon at this position here, and of course for a circle at the centre of the circle. But in general, what about a triangle? Well, this diagram shows a way of considering the triangle. Look at the baseline BC, and you can see that if you consider the triangle as being made up of lots of thin rods, then the position of each of the centres of mass of those rods must lie along this line here, which is actually what's called the median of the triangle. So the position of the centre of mass is along a median. And it will also be along any of the medians, so we can take the median from the line AB, and again it must lie along here because these are the centre points of each of the lengths of rod which are parallel to the side AB. So where the medians cross must be the centre of mass. So the centre of mass is where the medians meet, and that is known as the centroid. The centroid of a triangle is 2/3 the way along the median from any vertex. So this point here will be 2/3 of the way along, and then therefore 1/3 of the way from the base. Now we don't need to work with the slanting line in general, because if we put in some axes now along here, then that distance up from the origin will be equal to 1/3. So it's 1/3 from the base BC along the median. So if we have a right angled triangle going from O here, then we can say that the position of the centre of mass is going to be 1/3 of the way up from O in the along, so 1/3 of B, and also 1/3 from the left hand side. So the position at the center of mass here would actually be at 1/3 of A, so A over 3 and B over 3. For an isosceles triangle where we have a line of symmetry, so this here is the line of symmetry, we know that it must lie on that line of symmetry, and indeed it will lie 1/3 of the way up from that base. So using that idea of 1/3 of the way up from the base, look at this situation. If we look at OA, the base length here, then from this corner here we've got to come 1/3 of the way, so the center of mass must lie on this line here, where we split it in the ratio of 2/3 to 1/3, in other words 6 to 3. And then looking at the length AB, this side here, it must also be 1/3 of the way from A to B. So the center of mass is this position here, where we've gone up by 1/3 of 8, so that distance there is 8 over 3, and we've come here a distance 3, and this one here must be 6. So therefore the center of mass is at a position 6 in the x direction and 8 over 3 in the y direction. Well, sometimes we have problems where we've got a mixture of lamina and masses attached to a lamina. So this becomes relatively straightforward if we realize that the lamina itself can then be remodeled as a mass and at its center of mass of the lamina. So we consider the whole mass of the lamina as acting at its center of mass. And then we have a system of masses to deal with, which we've looked at in previous videos. So here's an example of that, where we've got a display board, and the display board itself has got a mass of 8 kilograms. And attached to that are some pots which are represented by points. So these are point masses: A 2 kilograms, B 1 kilogram, and C 1.5 kilograms. And we're given the positions of those relative to the origin here. So we've got the positions of the center of mass 7, 5, so this point here 7, 5. A is at 3, 7. B at 10, 2. And C 6, 4. So now we've got, in effect, a system of 4 masses. This diagram shows a situation then where we replaced the lamina by a point mass, and we can now proceed as we've done before with a table. So we've got masses of 8, 2, 1 and 1.5. M is at 7, 5, A at 3, 7, B at 10, 2 and C 6, 4. So if we first of all calculate MIXI, we get the values 56, 6, 10, 9, and that gives a total of 81. And for MIYI, we get 40, 14, 2 and 6, giving a total of 62. And the total mass is 12.5. So now we know that x bar is equal to sigma MIXI divided by sigma MI, so the sum of the moments in the x direction, which is 81 divided by 12.5, and that comes out to be 6.48 to 2 decimal places. And y bar is equal to the sum of the moments in the y direction, so sigma MIYI divided by sigma MI, and that's 62 divided by 12.5, which is 4.96 to 2 decimal places. So therefore we have that the coordinates of the centre of mass are at 6.48 and 4.96 relative to that origin that we had in the bottom left hand corner. In summary then, a uniform lamina has area and mass but no thickness, so crucially it's a two-dimensional object. For regular shapes such as hexagons, circles, rectangles, then we can find the centre of mass by looking at the lines of symmetry. For a triangular lamina, you need to know that the centre of mass is 1/3 of the way up the median from any side to its opposite vertex. And then if we've got lamina mixed with masses, then we can replace the lamina by a point mass acting at its centre of mass. Well, that concludes this video on centres of mass of uniform lamina. In the next video we'll consider centres of mass of composite bodies.